This video presents the paper entitled A Control Approach for Human-Robot Ergonomic Payload Lifting. In this work, it is presented a novel approach for human-robot collaboration based on partner awareness through the estimation and modeling of human action. This has allowed humanoid robot to perform payload lifting tasks in collaboration with human, synchronizing their actions and optimizing the overall system ergonomics. Historically, physical human-robot collaboration has been focused on safety, avoiding harmful collisions, and flexibility via compliant control strategies. Similarly, humanoid robots have been endowed with compliant control strategies. There are examples in literature in which humanoid robots can hold a payload with human partner using whole-body control strategies. Besides being able to achieve the task, the human action is modeled exclusively by measuring interaction forces. This means that the reciprocal effect of the agent's action into the partner state is not taken into consideration. In this work, we try to add the human in the loop during human-robot collaborative payload lifting, introducing some novelties: the use of wearable sensors for estimating the human state, the use of couple dynamics for modeling the interaction, and the definition of a single control framework that considers and optimizes both human and robot actions. In order to consider a human agent, we assume that the human body is modeled as a floating-base multi-rigid body system, with n degrees of freedom, representing the skeletal joints, while the action of the muscles is synthesized by the resulting torque acting on the human skeleton. Considering now a system composed of a robot and a human interacting with the same object, the couple dynamics defines a unique system of equations that takes into consideration dynamics of the three elements. This scheme summarizes the proposed control framework. The top part of the scheme shows a classical hierarchical control architecture used in robotics. In our framework, we assume that the subject interacting with the robot is monitored using wearable sensors. The data are provided to the human perception system, which is responsible of estimating online the human kinematics and dynamical state. Reference postures allowing the achievement of the given task are computed offline, optimizing the execution for both the human and the robot. The transition between the planned configurations is regulated introducing a free parameter psi and defining its dynamics in order to track the position of the human hands. The last layer is responsible of defining the robot motor commands in order to track the reference trajectories, maintain the balancing, and control the payload position. All those tasks are embraced by a single quadratic programming optimization that outputs contact wrenches and reference joint torques for the robot. Starting from the bottom, the optimization is composed of the following terms. The robot postural task tracks the reference robot trajectory computed by the trajectory adjustment block, while a reference zero dynamics for the human is given by gravity compensation. Then we have the couple dynamics constraint, which describes the dynamics of the overall system. Then, inequality constraints on the contact wrenches are used to guarantee their feasibility. This linear constraint represents the control of the robot and human momentum and the payload pose. Finally, in the cost, there is a term that regularizes the wrenches at the human feet with the measured contact wrenches, and a second term that minimizes the joint torques to optimize the force ergonomics. The proposed control framework was validated in an experimental scenario using the iCap3 humanoid robot and the iFeel wearable sensing system composed of 10 inertial nodes and a pair of sensorized shoes with force torque sensors. The experiments have been designed accordingly to robot capabilities, considering a payload of 4 kg and a displacement of 40 cm. On the right, it is shown the estimation of the human state, the measured robot state, and the desired robot configuration. In this first video, it can be observed the trajectory adjustment capability. The motion of the robot is adapted online accordingly to the intention of the subject, moving the payload upwards or downwards. This second video shows the compliance properties of the trajectory control strategy. The robot remains compliant while the subject tries to displace the payload from the desired position. This is made possible thanks to the presence of a whole-body torque control strategy. Thanks for the attention. Additional details can be found in the manuscript. Do not hesitate to contact me directly at the email address for further questions. While following the QR code on the right, you can find the code associated to this work.